Number 7, how many non-zero terms are required to estimate this expression within this much of an error? Anytime you're dealing with errors, there are 2 scenarios to consider. One is the alternate series remainder error, and this is the easier and faster one. But if it's not an alternating series, then we'll be using the Lagrange error bound. All right, so number 7, E's series should be memorized. It's one of the 4. Recall, you should have memorized the series for these 4 functions, including the first 4 terms, the general term, summation notation, and the interval of convergence. Since this series for E is not alternating, we will need to use the Lagrange error bound idea, which says that the magnitude of your error when you use the nth degree Taylor polynomial to evaluate some function at this x value will be no bigger than the first unused term of the Taylor polynomial. And what is the first unused term of the Taylor polynomial? The Taylor polynomial is generated by this formula, which generates these terms. When k is 0, this simplifies to f of c. When k is 1, 2 and 3 all the way to when k is n. So the first unused term is when this value is n plus 1. So this is the first unused term. I haven't finished everything yet. All right, let's pause for a second. Now this is the remainder when you evaluate the function at x. So the square root of 2 can be substituted in for x. In this series, e to the x's series is centered at 0, so we can put a 0 right there. There we go. And finally, it's kind of, the error bound is kind of the first neglected term, the first unused term, which is the n plus 1 term, except the Taylor theorem itself tells us that the remainder is exactly equal to this expression for some value of z between where we are centering it, which is 0, and where we're evaluating it in this case, which is the square root of 2. Taylor's theorem tells us that the remainder is exactly equal to this expression, the first unused term, for some z value here between where it's centered and where you're evaluating. Thing is, we can't find this z value. The Taylor theorem is an existence theorem. It guarantees that this z value exists between 0 and 2, such that the n plus 1 derivative there times the rest of the formula gives you the exact error, the exact remainder. But it doesn't tell us how to find it. So what we end up doing, the Lagrange error bound, what the Lagrange error bound ends up doing is saying, well, we can, if we can't find exactly what that z value is, let's just take the maximum of that expression on the interval from 0 to 2. And if that's the maximum, then we know if the exact value exists somewhere there. And if we just take the biggest, then we know that our remainder has to be less than or equal to that expression. And sometimes this difference ends up being negative. We're just trying to find the magnitude of the error. So there's actually an absolute value around there as well. All right, so this is all review. Hopefully this makes sense. We're going to find what is the n value. In other words, how many non-zero terms should there be so that our remainder is less than or equal to 0.0001. All right, let's go ahead and solve this, and we'll find out our value n, which will be the answer to this question. As you know, if our function is e to the x, the first derivative is e to the x, the second derivative of f is e to the x, every order derivative is e to the x, whose graph we know looks like this. And therefore, on the interval from 0 to root 2, the maximum value of that will happen at the endpoint, the square root of 2. So the maximum will be when x is the square root of 2. So whatever derivative will be, e to the radical 2 will be the maximum value of that derivative on this interval. Then we have root 2 to the n plus 1 over n plus 1 factorial, and we just need to solve this. This is a calculator problem. Enter this as a function and find out what n value will cause it to be less than or equal to 0.0001. So there's our error. It needs to be less than or equal to 0.0001. Too big. Too big. And finally here, when n equals 9. So if n is 9, does that mean there are 9 terms? You need to consider the series. We're talking about the series for e to the x, which is this. And so when you had the degree 1 term, there are really 2 terms already. For the degree 3 term, there is 1, 2, 3, 4 terms, one more than a degree. So if our biggest degree n of the used term, this is the neglected term, is n equals 9, then there'd be 9, 10 terms. There are 10 non-zero terms, which are required in order for this estimate to be within 0.0001 of the true value. How many non-zero terms for this series would we need in order to estimate this expression to within 0.0001 of the actual value? We would need 10 non-zero terms.